Assalamualaikum and good morning to everyone. So, my team will presenting our group project assignment for CSC510, which is a finite state machine. So first, I will introduce my group members. The first one we have Siti Khadijah binti Muhammad Amin, and then this is me, Nur Amnina Najah binti Ar Azmi, and we have Nur Firzasha Azurin binti Mat Yazid.
First, let's look at the background studies. A finite state machine, or FSM, is a mathematical model used to represent and control sequential system behavior. Its core mechanism is simple. It changes one state to another based on external input and specific transition rules. In discrete structure, the main type of FSM are divided into two: deterministic finite automata (DFA) and non-deterministic finite automata, that is NFA. Next, what is the operational difference between these two? And what is our objective? For DFA, every state has exactly one unique next state per input, which ensure a single linear execution path. On the other hand, NFA provide more flexibility, where a single state can branch into a multiple transaction for the same input, and it even allows transition without consuming any input, known as epsilon transition. Therefore, our project objective is to build a programming framework that automates this concept, allowing us to systematically evaluate their design and execution effectively. Moving on to the problem statement, there are four main challenges we identify. First, inefficient and error-prone manual tracing. Tracing string accepted manually is slow and highly prone to human error, especially with complex state structure. Second, complexity in handling transition path. It is very easy to make mistake when analyzing machine, such as misinterpreting concurrent branching path in NFAs or overlooking missing route in TFA. For the third one, we have poor scalability of hand calculation. Validating string by hand require extensive branch tracing, which scales poorly and highly impractical as the number of system states increase. And lastly, we have lack of automated diagnostic tools. There is a lack of integrated automated tools for students and analysts to instantly parse transactions rule and verify string compatibility without using manual step-by-step mathematical proof. Next, for the project scope, our FSM engine's application focus on five core areas. First, the FSM data input. The system support dual input methods, loading transition rule via text file or entering them manually via console. Second, automated classification. It automatically analyzes the data to verify whether the machine is DFA or NNFA. Third, string acceptance testing. User can evaluate any input string to see if it is accepted or rejected by the model. And for the fourth one, we have valid string generation. The system can list all unique valid string up to a user-defined length. And lastly, system architecture and constraint. This program is developed entirely as a text-based console application using C++, and it assumes that the starting state will always be S0, state 0.
So now these are the flowchart for our system, which is a finite state machine system. So once we start, once the system start, the user need to input the system options. They are either option 1 or option 2. If they choose option 1, they need to input the text file that already have the FSM lines in it. But if they choose option 2, they need to input the FSM lines line by line manually. So after they input the FSM lines, they need to input the final state. For example, S4. So that is the final state. And then once they are done, they need to input N to for both option they will be displayed with FSM summary. And then after that they can choose option 4 if they want to know the accepted string from based on the FSM lines that they have already input before. So they need to input maximum string length, for example 4 or 6, so they will be displayed the accepted string for the maximum string length they inputted before. So after that, they can choose option 5 if they want to see whether the result is accepted or rejected. So they can input a string for testing. For example, they can input A, B, and the system will display whether it is accepted or rejected based on the uh, FSM lines they have inputted before. And then they can choose option 6 to see whether their FSM is either NFA type or DFA type. So once they are done, the system will end.
So in this video, I will demonstrate our Finite State Machine FSM engine developed using C++ as a console-based application. So this is the welcome page of our system. So there is a main menu that will display all the available functions that user can perform. This include loading an FSM from a text file, entering an FSM manually through the console, displaying the FSM summary, listing accepted strings, checking whether strings is accepted or rejected, determine the FSM type, either DFA or NFA, and exit the program. So for this demonstration, I will use option 2, which allows user to enter the FSM manually through the console. So this is the data that I will enter. So I will choose option 2 and enter. And I will enter the data manually, and at the end of the line I need to type N. So here, after entering all the required data, it displays the FSM summary. So in the summary, the system successfully shows the information of the finite state machine, including the list of states, the input alphabet, the start state, the final state, and all the transition rules. So this summary allows user to verify that the FSM has been entered correctly before performing other operations. Next, I will choose option 4 to list all the accepted strings. So the system asks me to enter the maximum string length. So for this demonstration, I will enter 3. And the program then will generate all the accepted strings that satisfy the given FSM within the selected length. So this feature will help user to understand which input strings are accepted by the finite state machine. After that, I will proceed to option 5, which checks whether a given string is accepted or rejected. So for example, I will enter the string AB. So user need to type A blank space and B, and the program will process the input symbol by symbol following the transition rules from the start state until the end of the string. Since the machine does not end at the final state, which is S2, so the system will display rejected. Finally, I will select option 6 to determine the type of the finite state machine, either it is DFA or NFA. So I choose option 6. Then the system will analyze every transition in the FSM. Since each state has only one possible transitions for each input symbol and there are no multiple transitions for the same input from the same state, the system identifies this finite state machine as a deterministic finite automaton or DFA. So here the system will show the output, which is the FSM type. And for our demonstration, it shows that it is DFA, which is the deterministic finite automaton or DFA. So this concludes the demonstration for our finite state machine engine. So if user want to exit from the system, user just can choose 0. That will redirect them back to the blank page.
So, in conclusion, this project successfully delivered an automated tool for analyzing, classifying, and verifying the finite state machines. Through systematic testing, we demonstrated that while NFAs offer flexibility and power in pattern matching at a higher computational cost, DFAs provide the predictable linear determinism needed for structured system requirements.